Oh my gosh. Takes 27 minutes to settle. This is a great problem. I love this. Okay, so the first thing is we're going to find its terminal velocity. So velocity is 0.085 divided by 27 times 60, right? Because you want to get seconds. So my velocity is 0.085 divided by parentheses 27 times 60, end parentheses, 5.2469. And that's times 10 to the minus fifth. Wow, that takes a long time. Is that right? That's very slow. It's going to be a small drop. I guess it's not. Oh, it's basalt. It's basalt. Okay, there we go. Okay, so that is meters per second, right? Okay, and then it's falling through water. Okay, this thing is falling through water, and so what we have to do is as it falls through the water, we've got, of course, the Stokes force up. We've also got the buoyant force up. So we got this guy, and then the force down is just the weight of the thing, the mass times gravity, right? So let's set that up. I'm going to say this plus this is this, right? So 6 pi plus the buoyant force, which is rho of the fluid, volume of the chunk of basalt times g, and then that's going to equal rho of the basalt, volume times g. So this is the formula for buoyant force. Notice that this is the fluid, in this case the water. Okay, this is the density times volume is mass, right? And this is just the weight of the chunk of basalt, right? Now, if I just rearrange this ever so slightly, I'll get this. And it always works out this way, right? Everybody does this, right? So let's just keep going here, right? And then that is density. So basically, you just subtract this. This is the volume of the basalt. That's g. When you put it on this side, you can factor out the Vg and get this. Okay. So let's go basalt minus, and then the volume is, of course, 4/3. It's a sphere. Everything's a sphere. Okay. 4/3 pi r to the third, and then g. That's our volume, right? And now we're all set. Now we can what are we trying to? Oh, we're trying to solve its speed. We got its speed. We're figuring out its radius here. Okay. So let's. I think we can cancel out a pi, right? I think we can cancel out one of the r's. Can't we? Yeah, we can. And we end up with this 6 times right? And now we're trying to solve this for r, so we're going to multiply, what, I guess by 3. Is that right? Multiply 3 divided by 4, so 3 times 6 is 18, divided by 4 is 9, so we end up with 9 halves. Right, and then this guy goes in the denominator. The fluid, in this case the fluid is the water. G goes in the denominator here, and then that equals r squared. So I put this in the denominator, put that in the denominator. The 4 goes in the denominator, right, and the 3 goes in the numerator. So 3 times 6 is 18, 18 fourths is 9 halves, right? And then I guess what, we square root this, and then that's going to be r, right? So that is the square root of 9 times the viscosity of water. What is the viscosity of water? I do believe it's 1.002. Okay. The velocity is 5.2469. All right. and that's divided by 2 times 2920 minus 1,000. So if it's immersed in something that exerts a buoyant force, basically you can just do the same calculations you did when we ignored the buoyant force, only the density becomes the difference in the density. It always works out that way. Okay, my calculator got so bored with this problem that it's turned itself off. Okay, let's see if I can type it in. Okay, I'm going left, I'm going radical left parenthesis. It's a radical left parenthesis. 9 times 1.002 e minus 3 times the answer I just got, divided by parentheses. I got to put the whole denominator in parentheses. 2 times parentheses. 2920 minus 1,000 in parentheses times 9.81, ending the denominator, ending the radical. 3.54 times 10 to the minus 6. Yes. Yes. Okay. All right. Okay, so that's the end of the normal part of the problem, right? We got the velocity. We had to figure that out. Ultimately, we figured out the radius of the drop, okay? And then, now let's go into the paranormal part of the problem, which is we spin it up in a centrifuge like this. What I want you to see here is that the velocity, ultimately the velocity is proportional to the g, okay? So I'm going to hit erase here and just set this thing up because I need more space. Okay, so ultimately we ended up with 6 pi nu RV equaled density of the basalt minus the density of the water times the volume of this thing times g, right, which is ended up being density of the basalt minus density of the water times 4/3 pi r to the third times g. Now, if we cancel pi and we cancel one of the r's, right, and solve this for v. V is actually well, let's see, 6 times 4 is 18, or 6. Oh wait, we got to divide by 6. So this is going to be 2/9, right? Because it's 4 times 6 would go in the denominator, right? So it'd be 4/18 or 2/9, right? Okay, and then here we have and then we'd have r squared. We'd have g, and then these guys would be in the denominator. The viscosity. I guess it's just the viscosity. That's all that's left, right? Okay. Notice that I'm not going to actually solve this. I'm actually just going to bootleg this thing. I'm going to woodshed it. Okay. Notice that the velocity is proportional to the gravitational attraction, right? Okay. So if you double the gravity, you're going to take the velocity. You're going to double the velocity. Okay. In this case, we're going to have a lot more than that. So what I'm going to do is I'm just going to figure out the g-force. Right? Let's see, the g-force is going to be, centripetal acceleration is omega squared r, right? So that is, omega is 1200, 2 pi's over 60, right? Squared times 0.054. Okay, so here we go. Parentheses, 1200 times 2 times pi divided by 60 squared times 0.054. Okay, so the centripetal acceleration, which will be our new g-force, is 852.7. And if you wanted to, you could plug that in for g, solve for the velocity, then figure out how far how long it takes to go 8.5 centimeters. I'm not going to do that. I know that it's going to take that the time is going to be 27 minutes times 9.81 times divided by 852. Right? It's going to decrease by the proportion. This is the g-force that it took 27 minutes. I'm going to divide by that, and that'll give me the minutes that it takes, right? So 27 times 9.81 divided by the answer I got. I get that it takes 0.3106 minutes, which is ridiculous, right? So let's multiply by 60 and get 18.6 seconds. Is 18.6 seconds. That's a whole lot better than a half an hour, right? Okay, that's why we use centrifuges. Hope you're stoked about that. Ha ha!